to this video on chi-square test of homogeneity. By the end of this video, you should be able to state appropriate hypotheses and compute the expected counts and chi-square test statistic for a chi-square test based on a data in two-way table. You should be able to state and check the random 10% and large counts conditions for a chi-square test based on data in a two-way table. You should be able to calculate the degrees of freedom and p-value for a chi-square test based on data in a two-way table. And you should be able to perform a chi-square test for homogeneity. Alright, so today's scenario is about the distribution of gummy bear colors. We have Haribo gummy bears and Meyer gummy bears. Meyer is a grocery store in the north. Okay, so I'm going to give you the counts. We've got 175 red, 91 green, 105 yellow, 118 orange, and 105 white for Haribo. And Meyer had 160 red, 99 green, 107 yellow, 101 orange, 95 white. So go ahead and finish filling out the totals, and come back when you're done. All right, so looking at our table, we've got all our totals filled in. So how many samples do we have, and what population are they from? We have two samples. We have a Haribo sample and we have a Meyer sample. So there's two samples. One's from the Haribo population, and then the other is from the Meyer population. Okay. How many variables are we examining? Well, the only thing we're looking at is color. So we have one variable, and that's color. Okay. So this is a distinction. We did the chi-squared goodness of fit. The chi-squared goodness of fit is actually a one-way table. You just have one set and you're looking at one variable, one sample, one variable. Here we have this two-way table going on because we have different things going on. We have two separate samples and we have a single variable that we're looking at both of these. So this is a test called homogeneity, chi-squared homogeneity, and we're looking to see if they're the same, which is what homogeneous is. Homogeneous means the same. So we're going to write our hypotheses here. So for our null, that idea of sameness with homogeneity. So the color distribution is the same for Haribo and Meyer gummy bears. Okay, so for our null, we're saying there's no difference between them. Then for our alternative, we're going to say that it's not the same. We don't think that they're the same. All right, so now we have our null where they are the same, the distributions are the same, and we have our alternative where the distributions are not the same. All right, so now we're going to use the chi-square test to test whether there is a difference between the two populations. One thing that we need to be able to do that is the expected values. Now we don't actually know what a claimed distribution is, and so here's how we're going to find our expected counts that you're going to go back and fill out your table. So to find your expected counts, you're going to take the row total times the column total and divide them by the table total. Okay, so let's take a look what that's going to look like. All right, pull out your handy dandy calculator. Okay, so we're going to go back up to here. We're going to take our row total, 335, times our column total, times 594, equals, and divide by our table total of 1156 for a number of 172.1. So that would be for the Haribo red. 172.1. So you're going to go through each of these and you'll do each row total times the column total divided by the table total. And when you get over to Meyer, it's going to be the row total times the column total divided by this table total. So go ahead and fill out the rest of your table and come back once you finish. So this is what we would have expected if their distributions were the same. And so this is, we can find this, that this will always work to help us give us the expected value when you're not given a claimed distribution like we may have gotten when we did the goodness of fit test. All right, so let's go ahead and flip this over and move on to the back side. All right, so on the back, I just transferred our null and alternative hypothesis from the front. There's no anything that it says we're going to do an alpha 0.05. It's the most common for things that aren't life endangering. If you're endangering life or medical things, we tend to use the 0.01 to be a little more conservative. Okay, so our procedure, it's a chi-squared test for homogeneity. You could also write it chi-squared like that. You don't have to spell it out. So now let's check our conditions. For our random condition, we have 2 samples, so randomly selected, and we had 594 of the Haribo, and we had 562 of the Meyer. You need to address both of them. So if they're both the same, you can say there's 500, well, however many there are, but you need to be sure that you're stating it's for both of them. Without being explicit, that's not going to work. So our 10%, so 594 is less than 1/10 of all Haribo gummies. And then the 562 is less than or equal to 1/10 of all Meyer gummies. All right, for our expected counts, our large counts here. Normally I would say go ahead and make a table here with everything in it. We have already done that back over here. So normally you would make this table in your expected counts, but since we've done it, I'm going to say see the table in number 5, and remember all counts are greater than or equal to 5. That's our magic number when it comes to our expected counts when we're okay. And so please do not say this is normal. This is so the sampling distribution looks like chi-squared. Okay, so it's not normal. Please do not write that there. You'll get into trouble with that. Okay, so our specific formula, that's our chi-squared equals the sum of observed minus expected squared divided by expected. All right, and so let's take a look, and we're going to start setting this up. So we have chi-squared equals. Now you're going to need to go back to the other side so you can match these all up, but I'm going to get you started. So we had 175 red, but we expected 172.1 of them. So we're going to square that divided by 172.1 plus, then you had the next color, which when you go back was green. There was 91 of those. We expected 97.6 of them, divided by 97.6 plus, and you'll continue it and you can set it up with the last one. But remember, like goodness of fit, you may need to know some actual values here in order to do a follow-up analysis if we are actually significant here. So finish setting this up and come back when you're done. All right, so I've got the first two plus ... plus the very last one. This is enough work for AP and for me in order to get full credit. Make sure you're labeling everything. We are trying to get the chi-squared here. Now, I'm going to show you how to do this in the calculator because it's really the only way I want you to be doing this. There's too much chance to run into a problem if you're doing these all individually. Okay, so we're going to go into stats, go back over to tests like we were doing for our goodness of fit, and go up and you just want the chi-squared test. We don't want the goodness of fit because this won't work for it because that's really a one-way table and we have a two-way table. Chi-squared goodness of fit. And when you press enter, it says observed and then it's got a bracket with A. What they really want us to do is they want us to go put our observed values into a matrix. The expected values will go into a second matrix, but here's the really nice thing here is that expected values will automatically populate into that matrix for us. We don't have to put them in. So to get to the matrices, I want you to press, let's exit out of this, second, and then X -1. It's right here and it says matrix right above it. And you'll come up with these matrices. So we're going to go over to edit and enter. Okay, so let's look at our counts. What kind of table do we have? This is a 1, 2, 3, 4, 5 by 2 table. So let's change this. 5 by 2. Okay, and so this should kind of match what we've got here, that we had 2 wide and 5 deep. And then we want to go ahead and put, you can just type over whatever might be in there. So we got 175, enter, and it will automatically go to the next one. 160, enter. 91, enter. 99, enter. 105, 107, 118, 101, 105, and 95. So just go back and double check. Does this look like what we started with? Make sure you have the same values. Okay, once you've got the matrix A set up, we'll go back to stat and tests, up to your chi-squared, press enter. Now we've got our data in A, it will automatically populate B for us, so we don't have to worry about that. Go down and tell it to calculate. And here we go. We've got a chi-squared of 1.96. So we're going to go back to the other side. So we've got a chi-squared of 1.96. And that would give us a p-value of 0.74. 0.74. Okay. You can see it says degree of freedom there of 4. So here's how you find your degree of freedom. So it's the rows minus 1. So there's 5 rows minus 1. And the columns, there's 2 columns minus 1. So you get 4 times 1, which is 4. So it's the same idea of n minus 1, but because you have 2 different samples, you have to address for both of them. Okay, so our picture, remember our chi-squared is always skew right. So this is a chi-squared distribution with a degree of freedom of 4. Okay, and we got a chi-squared statistic of 1.96. So I'll label it on there. A p-value of 0.74. Okay, well, so that's a pretty big p-value. Means it's pretty common. What I would like you to do is take a minute and write a good conclusion. Remember, you want to make a decision, interpret your p-value. That's the assuming the null is true statement. Then you want to make a decision about your alternative and a conclusion about your alternative. We do not have to do a follow-up analysis, I'll give you that hint, because your 0.74 is bigger than 0.05. So we're going to end up failing to reject here. So no follow-up analysis is necessary. So go ahead and write that and come back once you're done. All right, so let's take a look, see how you did. Assuming the color distributions are the same for Haribo and Meyer gummies is true. We're assuming that null is true. There is a 0.74 probability of getting a chi-squared of 1.96 or greater purely by chance. Because 0.74 is greater than 0.05, we fail to reject the null. We do not have convincing evidence the color distribution is not the same for Haribo and Meyer gummies. Okay, so I wanted to show you another thing in your calculator for this expected counts. So we made the table on the front, but remember when we ran the test, it said the expected counts would be in matrix B. So I'm going to go back into matrix. So I'm going to go over to edit because it's a little easier to see if you look at it, the edit, and I'm going to look at table B. Here's all the expected counts. They automatically populate in for you in the same orientation as you would have done in your table, so they can match up directly what you've got. So in the future, when you're running your test and you need to check your expected counts, you can copy this table and say the entire table is greater than or equal to 5. So we could have had something like this guy drawn in our expected counts and just set it greater than or equal to 5, and then we would have been okay to move on, or we would have met our expected counts. Okay, let's turn all the way to the back and summarize. All right, so I have 3 major things that I want to make sure you walk away with this. We had a lot of learning targets in this lesson, as you heard at the beginning of the video. The first one that we want to talk about is the hypotheses. Okay, for your null, it's almost like a math lib. So our null is that there's going to be no difference in whatever our categorical variable is, the distribution of our categorical variable, and population 1 and population 2. So the null, no difference. So there's no difference in whatever our categorical variable distribution for population and population 2. And then for our alternative, we're going to go the opposite and say there is a difference. So just the opposite. There is a difference in the categorical variable distribution for population 1 and population 2. All right. The other thing I want to be sure you can take away is your expected counts. Okay. Remember that's your row total times your column total divided by the table total. Okay, so your calculator will get that for you, but you also should know how to get it on your own. And then your degree of freedom is the number of rows minus 1 times the number of columns minus 1. Okay. Now, as we're moving forward, how can we tell which test? There's one more of these that we're going to learn about, so we'll add that in later. So we learned about the chi-squared goodness of fit test. And today we talked about the chi-squared homogeneity. Okay, so how can you tell these apart when you're working them? So the goodness of fit is one sample and one variable. Okay, the homogeneity is going to be two samples because we want to see if they're the same. So between the two things, are they homogeneous means the same. Two samples, and we're only looking at one variable. Okay, so kind of keep these in mind. And your goodness of fit is a one-way table. And your test for homogeneity is a two-way table. So you can't accidentally do the goodness of fit as a homogeneity because the calculator won't let you work. They won't let you do a matrice, a 1 by matrice. Okay, so what I want you to do, try the check your understanding, check the key. Let me know if you have any questions, and I'll see you in class.